In this lab, we will be learning about properties of light as it interacts with its surroundings. Light is a form of electromagnetic radiation that travels in rays and is measured from an imaginary perpendicular line to where the ray meets the surface. The angle a ray strikes a reflective surface is known as the angle of incidence. It will bounce off of the surface at the same angle but in the opposite direction, known as the angle of reflection. This is known as the law of reflection. When a ray is pointed at the intersection of two media, for example water and air, the light will change direction. This is known as the law of refraction. The angle of incidence is the angle of the ray as it passes from the first material into the next. The angle of refraction is how far the angle bent in the second material. These two values are related by Snell's law. To the right is a visual example of Snell's law, as well as it written out in formula. Snell's law states that for a given pair of media, the ratio of the signs of angle of incidence and the angle of refraction is equal to the refractive index of the second medium with regard to the first, which is equal to the ratio of the refractive indices of the two media, or equivalently to the ratio of phase velocities to the two media. In this lab, we will mostly be focusing on the signs of the angle of incidence and the angle of refraction and the ratio of the refractive indices. We will use the law of reflection in order to measure the percent differences between the incident and reflected angles of three different surfaces: a plane surface, or a 180-degree surface, a concave surface, and a convex surface. For the second part of the lab, we will use Snell's law to compute the refraction index of an acrylic prism that we have within our materials.
This is materials for Lab 10. For our first letter A is laser ray box, which is the little rectangle black box. It had multiple layers on the side, as you can see from the circles. But what we did is we taped post-it notes over them so that way only the middle laser came out, and we used that middle laser to focus on our angle and then see the refraction that came out on the other side. Our B was a three-way mirror. It's in the shape of a triangle with a straight side or a straight edge, a concave edge, and a convex edge. Um, our C were the protractors that we had. So using the laser, we used our protractor to measure the angle of the laser and then to also, so we could draw where the laser was pointing out so we can again measure better. Our D was our prism, so that's our second part, our step two of what we used to see the refraction in the prism. And then E and F are the paper. E is the paper that we use for our triangle that just gave us the sides, the straight, convex, and concave side. And then that's the paper where we drew the refraction, the way the laser was going in, and then the refraction out so we could see better. And then the same thing with F. It's the paper with the shape of the prism. So we align the prism on top of the paper and then from there draw out how the light refracted.
For this part of the lab, we focus on how light reflects off a mirror. First, we identified the normal line, which is the imaginary line that's perpendicular to the mirror surface. Using auxiliary page 1 and the three-way mirror, we traced both the incident ray and the reflected ray. We measured each angle from the normal, not from the mirror itself. Then we recorded three different angle measurements on each side of the mirror. After collecting the data, we calculated the percent difference for each pair of angles and used those values to find our average percent difference. That average represents our measurement error for the reflection portion of the lab. Next, we moved on to the refraction using the acrylic prism. With auxiliary page 2, we measured how the light ray bent as it entered and exited the prism. We repeated the experiment twice, using two different incident angles so we could compare our results. Using Snell's law, we calculated the refractive index for each trial and then averaged the two results. After that, we looked up the accepted refractive index of acrylic and used it to calculate our percent error. This helped us see how close our experimental value was to the real value and how much error comes from our measurements.
So for the very first experiment, as we discussed in the procedure, we measured the incident angle, so angle that's coming in, and we then measured the reflected angle, which is the angle that's reflected off the mirror. By the way, we used a three-way mirror. The diagram is available on the top right side of the screen. And as you can see, there was three sides: plane, concave, and convex. And plane, as discussed in class and as expected, had 0% difference between the incident and reflected. Concave, on the other hand, had a negative 5 degrees for the reflected compared to the incident. But percent difference, it's consistently inconsistent. It had a 17% difference for 30 degrees, 11% for 45 degrees, and 8% for 60 degrees. Convex, on the other hand, compared to concave, was just plain inconsistent. For 30 degrees, it had negative 1 degree, which gave us a 3% difference. For 45, there was a plus 3 degrees, which gave us a 6% difference. And for the 60 degrees, there was no difference. When 60 was reflected, it gave us a 60 degrees. And so far, for the convex, the average difference, percent error was 3%. And we gathered all these percent differences and we averaged it out, and it gave us a 5% difference. So for the second experiment, our ultimate goal was to find the refraction index of the acrylic. And the acrylic and the shape of the acrylic is shown at the top right. And how we conducted this is that we shot two laser beams at two different angles at two different times. And we measured the incident angle, which is the angle in which the light entered the acrylic. And then we measured the refracted angle, which is the angle in which the light escaped or exited. And so we did this 2 times, and we got the angles for both attempts. And we used the formula at bottom right, and ultimately got the refraction index for the acrylic 2 times. And for the first attempt, we used 30 degrees, and we got the refracted angle of 33 degrees. And we used the formula on the bottom right, and we got N acrylic 1, or the acrylic refraction index at attempt 1 is equal to 0.918. And for the second one, we got 1.021. So after getting the two different indices from two different attempts, which was conducted at two different angles, we averaged those two out, which we got as 0.969. And we use that as our experimental index. On the other hand, our theoretical index is 1.49, or close to 1.5. Since there was a big discrepancy visually or numerically, we decided to use percent error. We decided that we would get percent error by using the formula. Percent error is equal to absolute value of experimental minus theoretical or actual over theoretical or actual times 100. And then furthermore, we got 34.7% error.
In conclusion, this experiment demonstrated the law of reflection by showing that the angle of incidence always equals the angle of reflection when measured from the normal line. It also reinforced the importance of accurate ray tracing and angle measurement, which are essential for future studies involving refraction and refractive index. Overall, the lab strength or understanding of how light behaves when it reflects from a surface.